As Java developers, we often use both arrays and generic types in our code. But we usually don't go deep enough to understand the differences. In this video, let's take a look at the two critical differences between a Java array and a generic type, and also get some insight into the inner workings of these structures. In the whole video, a list interface is taken as an example of a generic type, but the discussion is very much relevant for any generic type. Here's an example of using an array in Java. We use square brackets to denote an array. Pretty straightforward. Here's an example of using a parameterized type in Java. Here we are using list of integer. At this point, let's get the naming right. The list of E is an example of a generic type in Java where E is the type parameter. List of integer, list of string, etc. are called parameterized types for that generic type. They have the real types embedded in them: integer, string, and so on. You can see that both arrays and lists are very straightforward to use as long as we are dealing with a single type. Let's now see the differences between the two. Arrays are covariant. Now what does this mean? Sounds scary, but all it means is the following. If class A is a subtype of class B, then array of type A is a subtype of array of type B. The example on the screen shows an integer array being treated as an array of numbers. Class integer extends from class number, so as per the covariance rule, integer array extends from number array, which is why there is no cast when assigning variable pair to variable nums. Generic types, on the other hand, are invariant. Now this sounds equally bizarre. Here's what it actually means. If class A is a subtype of class B, then list of A type is neither a subtype nor a supertype of list of B type. In other words, one cannot be assigned to another. Here's an example. In this example, it is trying to assign a list of integer to a list of number. Of course, this fails with a compile error because even though class integer extends from class number, the list of integer type does not extend from list of number type. So what is the primary benefit of array covariance? The big benefit of array covariance is that the elements of the array can be treated in a generic way as long as we are just reading from the array. To illustrate this, on the screen you see an example. Here we have created a method called sum, which takes in a number array as a parameter. Within the method sum, we treat the elements as a number and everything just seems fine. The method itself sums up all the numbers and returns a double. Now because of the covariance property of arrays, we can pass a variable of type number array, integer array, float array, etc. And the code works just fine. In the example code where it actually calls the sum, both examples are able to print the sum correctly. They use integer and float arrays. However, this benefit of covariance for arrays comes at a price: reduced type safety. We will see this problem in a minute. From JDK 1.5, when Java generics was introduced, array covariance is less important because the same can be achieved using Java generics. We will see that also in a later slide. Now let's look at the main problem with array covariance. The big problem is that if not used correctly, it leads to runtime problems. Consider the piece of code on the screen here. Integer array pair variable is treated as a number array by assigning it to nums variable. Since float extends from number, we can set a float, here say 1.2, to the index 0. Note that there is auto boxing going on over here. Now this line of code compiles fine, but at runtime the JVM throws an array store exception. This is because the JVM recognizes that the variable nums is actually pointing to an array of integer, and so it will disallow assignment to float, but this happens during the runtime. A formal way of saying this is that the arrays are reified. Their type is known at runtime, and the JVM tries to enforce the type safety at runtime. This is true of other Java types like primitives, int, float, or non-generic types like integer, float, or any other class without a type parameter. However, as programmers, we would rather have problems show up at compile time rather than at runtime. Now let's take a closer look at generic type invariance. The main benefit that we saw for arrays do not extend to generic types like list of E, because generic types are not covariant but invariant. However, the advantage of being invariant is that most problems are caught at compile time. In fact, we saw earlier an example of a compilation error when talking about the invariant property. You see that on the screen. Java Generics was basically designed for compile time safety, and that's a good advantage for developers. The compilation error eliminates an entire class of runtime class cast exception errors, which would have otherwise occurred. Going back to the example on the screen, this method sum can only be passed a variable of type list of number type. What happens if a list of integers is passed to it? It will fail with a compiler. That's expected because list of integer is not a subtype of list of number. But then how do we remove this irritating problem? One way is to use generic methods. Here we see a method sumList, which is a generic method. T is declared to extend from the number class within the angular brackets. This means that any variable of type list of a class extending number can be passed to this method. In the body of the method, you see that we are treating the elements of the list as a number. Now this gives us the benefit of generalization, but with the added advantage of being type safe. We cannot simply add any item to the nums list, and this makes it type safe. This solution, which is using a generic method, works fine. But the syntax for the method declaration is kind of verbose. A much more concise syntax is achieved by using wildcards, which is also the preferred approach by the language designers. Here is a method called sumListWild, which uses wildcards. A wildcard is basically denoted by a question mark, and you can think about this question mark as an unknown type. In the example, we are using the upper bounded wildcard. You see the nums parameter is declared as list of question mark extends number. That's the upper bound. The upper bound of the hierarchy is number. In plain English, this means a list of an unknown type which extends number. We actually don't give a name to this type, but since it extends from number, we can treat any element of that list as a number type. Why does this example on the screen actually work? Because list of number, list of integer, list of float, all of these are considered subtypes of list of question mark extends number. That's why we can now pass these types to the method sumListWild. Now we see that in the example where list of integer is passed as a parameter and the result is 300. As mentioned before, the generic types are designed for type safety at compile time. In fact, each generic type Java source file compiles to a single class file. For example, the list generic type is compiled to a single class called list.class and is shared by all of the parameterized types, list of integer, list of string, etc. What this means is that at runtime, the type information is actually stripped out from the list class. List class only has reference to the object class. There is no notion of E, which is the type parameter. But the compiler makes up for this by adding casts everywhere where the methods are used. The technical term used for this is type erasure. Generic types in Java are implemented using type erasure. Now let's switch back to arrays. Earlier we mentioned that the covariance rule for arrays is convenient, but it does open the door for runtime errors. This rule was created before JDK 1.5 when there were no generics and should be now considered as historical. The reason it is still there is to support backward compatibility with old Java code. With the introduction of Java generics in JDK 1.5, the same result can be achieved by combining arrays with generics, although in a type-safe manner. On the screen you can see the code to sum up all the numbers in an array. Here we declared the type of array to be a generic type parameter t, and also declared the type to extend from number. Now this code is type safe because within the method SumArray, we cannot add any item unless it is proven to be of type t. You can see that SumArray is called with an integer array as well as a float array, and both work fine. So by now, we know the two main differences between arrays and generic types. Arrays are covariant, generic types are invariant. Arrays enforce element type at runtime, which is reified, and generic types enforce their element type at compile time, but not runtime, due to type erasure. So what happens if we use both? Can we do something like what you see on the screen? Basically, can we create an array of a parameterized type? No, this is totally disallowed by the compiler and will throw a generic array creation error as shown below. Now to understand why this is disallowed, consider the following code on the screen. I have shamelessly taken this code directly from the book Effective Java by Joshua Block. Let's say the line 1 is possible and that it does not throw a compile error. In reality, it does throw a compile error. We are looking at a hypothetical situation here. At line 3, we are assigning variable strings to object array variable objects. Why can we do this? Because of the covariance rule. Now that it is an object array reference, the 0th index is now assigned to a list of integer objects at line 4. At line 5, we then extract the first element of the first index of strings array. The compiler will automatically insert a cast to convert to a string because that's what it is expecting. This will now throw a class cast exception because here the runtime is expecting a string, but what comes out is an integer, and the developer was not even warned about this. That's the reason why line 1 is actually disallowed, because it kind of breaks the Java generics rule. I hope this has given you a good insight into some of the main differences between a Java array and a generic type. If you like this video, give a thumbs up and don't forget to subscribe to this channel for some more quality content.